Welcome. Today we're doing a deep dive into MiniMax-Speech, which is a really interesting development in text-to-speech.
It is. We're looking at their research paper, the MiniMax-Speech.pdf.
Right. The paper lays out the architecture, the capabilities, and our aim here is to really understand what advancements MiniMax-Speech brings to the table, for high-quality, versatile speech synthesis.
And one of the most intriguing aspects right from the start is this ability it has.
You mean the voice cloning?
Yeah, cloning voices from just a short audio clip, and critically, without needing a text transcription of that clip.
Which they're calling intrinsic zero-shot voice cloning. It sounds quite different.
It is. And the core innovation, the thing that makes this possible, according to the paper, is their Learnable speaker encoder.
Okay, so unpack that. How does this learnable speaker encoder work?
Well, the research explains it's used to directly extract the timbre features the unique sound quality of voice just from the reference audio.
Just from listening to it, essentially.
Yes. And that's a contrast to, more traditional one-shot methods. Those usually required both the speech sample and a transcript of what was said in that sample.
So MiniMax-Speech is figuring out the voice's sonic identity directly from the sound waves.
Yeah.
Without needing the words matched up. What are the advantages there? Not needing the text.
The paper points out a few key benefits.
Mm-hmm.
First, it helps with cross-lingual synthesis because the voice identity isn't tied to the language in the reference audio.
Ah, okay. So you could use an English voice sample to generate, say, Spanish speech.
Potentially, yes. And it also sidesteps issues where, the provided text and the speech in a reference pair don't perfectly align. That can cause problems.
That makes a lot of sense. It's focusing purely on the voice characteristics. And this encoder, it's not like a pre-trained module they just plugged in.
No, that's important. The paper emphasizes it's trained jointly with the main TTS model.
Meaning it learns alongside everything else.
Right, so it becomes specifically tailored for the task of text-to-speech synthesis, which the researchers argue leads to, better integration and performance compared to using some generic, pre-trained speaker ID model.
Okay. The paper also talks quite a bit about audio quality, mentioning something called Flow-VAE. What's that about?
Flow-VAE, yes. They present it as an enhancement over standard variational autoencoders, or VAEs.
VAEs are pretty common in generative models, right, for learning representations?
They are. The idea here, as I understand it, is that the Flow-VAE combines the VAE structure with normalizing flows. Think of the VAE providing a sort of compressed blueprint of the audio.
Like a rough sketch.
Sort of, yeah. And then the flow model component refines that representation, allowing it to capture more intricate details. The claim is this leads to better audio quality overall and better speaker similarity, too.
So it's adding layers of precision to the sound generation. The paper also noted, I think, that the flow matching part operates on continuous speech features, not Mel spectrograms. Why does that distinction matter?
Right. Mel spectrograms are these visual representations of audio, very widely used, but the researchers suggest they can sometimes act as a bottleneck, potentially losing some subtle information from the original audio signal.
Ah, okay.
By working directly with the latent continuous features derived by the model, they might be preserving more of that fine-grained detail, which could contribute to the higher fidelity they report.
Let's circle back to the voice cloning. You mentioned intrinsic zero-shot. But the paper also discusses one-shot. Can you clarify the difference in this context?
Yes, they draw a specific distinction. For MiniMax-Speech, zero-shot means synthesizing speech in a target voice using only a reference audio segment. No text needed for that reference.
Got it, just the sound.
Just the sound. Then one-shot cloning is presented as an optional enhancement. It involves providing an additional prompt, specifically a paired text audio sample from the target speaker.
So one-shot uses a bit more information. A specific example of the voice saying certain words.
Correct. And they make a point in the paper that some other models described as zero-shot actually rely on this kind of paired prompt, which, by MiniMax-Speech's definition, would make them technically one-shot.
Interesting distinction. So MiniMax-Speech's foundation is really built for this powerful zero-shot capability. What does the paper claim are the big advantages of that zero-shot approach?
They list several. Obviously, the text-free reference is key. It means the speaker identity is learned purely from vocal characteristics.
Not tied to specific words or phrasing in the prompt.
Exactly. Which they argue allows for richer, more natural prosodic variation when synthesizing new text. It's not anchored to the prosody of the one-shot prompt. Plus, it supports robust cross-lingual synthesis, as we discussed, and provides a strong base for future extensions.
Okay, let's talk performance. The paper goes into quite a bit of detail on evaluations. What did the objective metrics like WHERE and SIM show?
Well, they tested on the TTS evil dataset. One key finding was that MiniMax-Speech actually achieved a lower word error rate, meaning better intelligibility, in its zero-shot cloning mode compared to some other models, and even compared to its own one-shot mode in certain setups.
That's counterintuitive, perhaps. You'd think more information in one shot might lead to better clarity.
It is interesting. The researchers suggest the zero-shot freedom might let the model generate more natural rhythm and intonation for the target text, improving overall understandability. And the speaker similarity, the SIM scores, for zero-shot were reportedly very close to the ground truth audio.
So it sounds like the target speaker and the words are clear. What about human listeners? Subjective tests.
Those results were quite strong, too. The specific version they tested, Speech Auto 2 HD3, actually reached the top position on the Artificial Arena TTS leaderboard at the time.
That's a public leaderboard where people compare different TTS outputs, right?
Yes. It indicates a strong preference from human listeners for its naturalness and expressiveness, even when compared against models from, major tech companies. The paper notes the zero-shot system outperformed others that might use much more speaker data.
And this performance wasn't just in one or two languages. They tested broadly.
They did. Multilingual evaluations across 24 languages. The results showed MiniMax-Speech had worse scores that were comparable or sometimes better than a strong baseline like 11 Labs Multilingual V2, especially in tonally complex languages.
And speaker similarity across languages.
That's where it showed a marked advantage. The SIM scores for MiniMax-Speech were significantly higher, consistently across all the tested languages.
That really does seem to highlight the effectiveness of that speaker encoder in capturing the voice identity, regardless of the language. What about specifically testing cross-lingual synthesis, using a voice sample in one language to speak another?
They evaluated that too. And again, the zero-shot approach showed its strength. Lower WHERE was achieved in zero-shot cross-lingual synthesis compared to the one-shot version,
Reinforcing that idea of decoupling the voice timbre from the language itself.
It seems to demonstrate that, yes, the encoder effectively captures the voice, allowing it to be applied to different linguistic content.
The paper also included an ablation study, didn't it? Looking at different ways to incorporate speaker information.
They compared their Learnable speaker encoder against alternatives, like using pre-trained speaker embeddings, or just relying on the audio prompt in the one-shot setup without the specialized encoder.
And the takeaway.
The Learnable speaker encoder came out on top, providing the best balance between low WHERE good intelligibility and high SIM sounding like the target speaker. This held true for both zero-shot and one-shot modes.
And one last check on the components, the Flow-VAE part.
Yeah.
Do they specifically evaluate its contribution?
Yes, they compared Flow-VAE against a standard VAE setup. The Flow-VAE showed advantages in both tasks. Vocoder resynthesis, which is like accurately reconstructing audio, and in the end-to-end TTS synthesis. Listeners also perceive the Flow-VAE output as more stable.
Okay, so the architecture choices seem validated by these tests. Now, the paper also touches on extensibility ways to build on this foundation. What did they explore?
They demonstrated a few extensions. One was emotion control using LoRA, low-rank adaptation.
LoRA is often used for efficient fine-tuning.
Right. Here, they trained separate small LoRA modules for discrete emotions like happy, sad, angry. This allowed for precise emotional expression without retraining the whole model. They also looked at how different types of reference audio, like emotionally matched or neutral, affected the output.
So adding layers of control. What else?
There was text-to-voice, or T2V. The idea here is generating a voice timbre not from an audio sample, but from a text description.
Like generated deep male voice with a slight British accent speaking quickly.
Something like that, yes. Combining natural language descriptions with structured attributes like speed, gender, pitch. They used techniques like PCA to compress timbre representations and trained a model to map the descriptions and attributes onto these representations.
That sounds quite ambitious, generating a voice from words alone.
It's definitely pushing the boundaries. And one more extension mentioned was professional voice cloning, PVC.
How does that differ from the zero-shot or one-shot we discussed?
PVC is about high-fidelity cloning for a specific speaker using parameter-efficient fine-tuning. Instead of full fine-tuning, they optimize just a small, learnable, conditional embedding for that speaker, keeping the main model frozen.
So less computationally expensive than retraining, but more tailored than zero shot.
That's the idea. Potentially beneficial for speakers with strong accents or unique vocal styles where zero shot might not be quite enough, offering scalability and efficiency. They mentioned applications like personalized educational tools.
Okay, so summing up MiniMax-Speech, the key strengths seem to be that learnable speaker encoder enabling robust, intrinsic zero-shot cloning.
Right, without needing text prompts for the reference audio.
The high-quality audio generation thanks to the Flow-VAE architecture.
Leading to good objective scores and strong subjective preference.
And its impressive performance across many languages in cross-lingual tasks, and its versatile extensibility for things like emotion control or text-to-voice.
It certainly presents a compelling set of advancements based on the research paper.
It does. Thank you for walking through the details of the MiniMax-Speech paper with us. It provided a lot to think about regarding the current state and future directions of speech synthesis.